Now ECE 351 fits right here. It's one of the courses you take right after you take Circuits 1. It's a required course for electrical engineers, an optional course for computer engineers, and generally useful for everyone. And what I want to talk about today would be inductors, kind of go along with capacitors that we talked about last week, and also a different equation called the wave equation. Similar to the heat equation, only different. So starting out, inductors are sort of like capacitors. They store energy. The difference is inductors store energy in magnetic fields rather than electric fields. The units for inductors are henries, and if you take a wire and wrap it into a coil, that produces an inductor. If you just have a straight wire, you're producing a magnetic field. Anything that has a magnetic field has energy and is an inductor. As an example of size, suppose I have a coil that's got 100 windings, 36 gauge copper wire, cross-sectional area is 25 millimeters, and the length is 10 millimeters. The inductance, going from Wikipedia, is a term called the permeability. That's a constant, 4 pi times 10 to the minus 7 henries per meter, times the number of turns squared, times the area of the inductor, divided by the length. So if you did that, this would be a 31 microhenry inductor. That's fairly typical. Like capacitors, inductances are rarely up to 1 henry. Microhenries, millihenries are fairly common. You can actually buy 10 henry inductors, but they're fairly heavy, like 5 pounds. With all that wire, that also produces resistance. For example, this one would have a resistance of 2.77 ohms, and that too is typical of inductors. You always have a resistance, because they have a lot of wire to make those coils, along with the inductance. So inductors are slightly different than capacitors. Capacitors are pretty close to ideal. Inductors, you've always got this extra resistance. It's not just a coil that makes inductance. If I have a long wire, like the transmission lines, that also produces inductance. From Wikipedia, the inductance is mu naught times 2 pi over L times length of the wire times A times minus B times plus C. Plugging in numbers, if I have a 1 kilometer long piece of wire at 60 hertz, it is 2.3 millihenries per kilometer. Doesn't seem like much, but when you have 1,000 kilometers of wire, it does add up. Now the BI characteristics for inductor are as follows. The energy stored in an inductor is related to the current. It's 1/2 Li squared. From that I can get the BI characteristics. If I take the derivative of energy, I get power. That's in watts, or joules per second. Take the derivative of 1/2 Li squared. Assuming L is constant, I get Li di dt. Power is also volts times amps, so canceling the current tells you what the voltage is. The voltage across an inductor is L di dt. So inductors act as differentiators, as opposed to capacitors, which act as integrators. What that means is if I have current versus voltage, say the current is the red line, the voltage across the inductor will be L di dt. If the inductance is 1 henry, it'll just be the derivative. So right here, the slope is 0, the voltage is 0. As the current goes up, I'll have 3 volts across the inductor. Current is constant, voltage is 0, so I can't have current even with no voltage drop. What the inductor cares about is the change in current. If the current starts to drop with a slope of -1, the voltage goes to -1, and then goes back to 0. So again, inductors are differentiators. Inductors also lead into the wave equation. Now as a recap, what we covered last week was the heat equation. The heat equation covers things like an RC circuit. If I have a single capacitor, this satisfies a first order differential equation. Again, I know it's first order because there's only one way to store energy. For this circuit, the current of the capacitor is C dV dt. That current is a current from the left, V0 minus V1 over 30, minus the current through the 150 ohm resistor, minus V1 over 150. Plugging in numbers, I get this first order differential equation. If we go to n elements, I wind up with a couple of first order differential equations. That gives the heat equation that we talked about last week. This week, we're looking at the wave equation. The wave equation are coupled differential equations, but instead of being first order, they're now second order. And that little difference right there makes a huge difference in how they behave. For example, if I just have a mass spring system, here I've got a spring. As I pull the mass to the right, the spring pulls me back left. If I compress the string, push the mass left, the spring pushes me right. So the force from the spring is your spring constant 10 times the displacement. Plus if I add a force to it, the net force on the mass is going to be F minus kx. Force is mass times acceleration. If I now solve for x double prime and plug in numbers, I have x double prime is minus 50x plus 5 times the force. I get a second order differential equation. If I cascade a whole bunch of masses together, what I wind up with at any given mass, like mass 2, mass times acceleration is the net force. The force from the left is going to be the relative displacement x1 minus x2 times the spring constant, plus the force from the right will be x3 minus x2 times its spring constant is mass times acceleration. Group the terms together, I now have something very similar to the heat equation, except that now it's the second derivative. That's basically what the heat or the wave equation is, coupled second order differential equations. That looks innocent enough, but it does have a huge difference in how it behaves. The wave equation is important because it describes a large number of systems, for example, a guitar string, cars stuck in traffic, buildings swaying during an earthquake or windstorm, transmission lines galloping on windy days, bridges oscillating, and so on. If I took this guy and pulled the mass back and forth, it would start bouncing, start oscillating. That's kind of typical of the wave equation. And here's a couple examples. The first one are galloping transmission lines. This is a windy day, and the wind is inducing oscillations in line, and see them bouncing up and down. That causes trouble. If they touch the ground, you get a big spark. If they hit each other, you get a big spark. Them bouncing up and down can cause metal fatigue. And this is basically just a mass spring system. I've got a spring constant from the tension. I've got mass. Each section line's got some mass. And I have an exciting force, the wind, causing it to bounce up and down. So this is a study done by civil engineering. Traffic also satisfies the wave equation. What they're doing is they set up a little course, basically a circle, and ask people to drive around it. What you have is the car, the accelerator's acceleration. The force on it is proportional to distance. You look to see where the car ahead of you is. If it's far away, I accelerate. If it's close, I brake. So acceleration is based upon distance. It's like a spring. And what you wind up seeing are wave patterns. And this also satisfies the wave equation. One of the all-time classic examples of the wave equation is the Tacoma Narrows Bridge. This is in I think in 1940. The wind is blowing very hard. What that does is that sets up oscillations. The bridge satisfies the wave equation. I've got mass. You think of this as a bunch of fine elements. I've got mass for each section of the bridge. I've got spring. As I twist the bridge, that applies force to the next element. If I excite it, I'm getting traveling waves. And of course, you can see from here, this is not good. Eventually, the bridge collapsed. And skyscrapers satisfy the wave equation. Again, this is like a big mass spring system. Take a skyscraper, pull it over. It'll start swaying back and forth. This is the skyscraper swaying on a windy day. Not that much fun for the residents. If you have an earthquake and the oscillations get too large, that's when the skyscraper will collapse. So those are examples of mechanical systems that satisfy the wave equation. You can also build electric circuits that satisfy the wave equation. To do that, I use inductors. Take the same circuit we had before, replace the resistors on the left and right with inductors, and now suddenly I have the wave equation, a couple second-order differential equations. And this actually models physical systems. This would be like a transmission line. This is 1 kilometer transmission line, produces 2.3 millihenries. The transmission line to ground is the parallel plate capacitor. And if there's some corona discharges, I've got a little bit of resistance, energy lost. So this will be modeling 1 kilometer of the transmission line, another kilometer, and so on. This also models a circuit board. If I have a circuit board, any piece of wire is an inductor. It's not much, but it is there. If I have the trace going to the ground plane, I've got a parallel plate capacitor. Plus the copper has some losses in it. So this is a model of extremely large systems, like the nation's transmission lines, and extremely small systems, like a circuit board. The differential equations that describe it are as follows. For an inductor, V is L di dt, so the voltage across the inductor, V1 minus V2, is L di dt. This voltage, going right to left, is V3 minus V2, is L di dt. And for capacitor, the current, IC, is C dV dt. So I have 3 coupled first-order differential equations. If I combine them, I get the wave equation. And the trick to combine them is take that third equation, take its derivative, and dot here means derivative, 2 dots means second derivative. I dot, I can substitute, is V1 minus V2 over L1. I2 dot is V3 minus V2 over L2. And I now have, by grouping terms, the second derivative of V2 is a function of V1, V2, and V3, where I misspelled V3, and V2 dot. That is the wave equation. Same thing we had for the heat equation, but now it's in terms of the second derivative. If I want to see how this behaves, a couple ways to solve it. This is actually a fairly hard problem to solve analytically, but numerically it's not too hard. I just use MATLAB and numerical integration. If I can solve for the second derivative, then I can integrate once and get the first derivative. Once I know the first derivative, integrate again, I get the voltage. Once I know the voltages, I know the second derivative, and repeat. So for this circuit, if I have a 3-node circuit, I would write the node equations at V1, V2, and V3, and notice again it's very similar to the heat equation. At node 1, I'm a function of my neighbors, V0, V1, V2. At node 2, a function of the neighbors, V1, V2, V3. Likewise at V3. Plug in numbers, and these are the differential equations that describe that circuit. Now to solve, I would use MATLAB. Same thing we did before. I calculate the second derivative. Integrate once, I get the first derivative. Integrate twice, I get the voltages. And then plot the voltages versus time. Now if you recall, the heat equation was just a nice, well-behaved, I just heat it up and then reach steady state. Wave equation is very, very different. I let this guy go and it doesn't settle out. It keeps on oscillating. It's a very different behavior. It's a little bit easier to see what's happening if I simulate it and plot the node voltages versus time. And it's more fun to let it run in MATLAB. So here, taking this 3-node equation, again, I calculate the second derivative based upon the voltages, integrate to get the first derivative, integrate to get the voltages, and then plot the voltages versus time. And here's what it looks like. The previous graph was just showing the time versus voltage. Here you can see it bouncing back and forth. Again, very different behavior than the heat equation. That's just for 3 nodes. With 3 nodes, it's really hard to tell what's happening. So let's repeat with 30 nodes. With 30 nodes, I have 30 coupled differential equations, which sounds kind of intimidating, but the first 29 are almost all identical. So that means a for loop. I'll just use a for loop, calculating for I equals 1 to 29, the second derivative. The last node's a little bit different because I only have one inductor attached to it. So it's like the heat equation. Same for all of them. Last node's slightly different. If I simulate this, this creates a traveling wave. Hence the name wave equation. If I take the input and snap it, a wave gets launched. So for example here, this is the 30 nodes, and I've got a for loop right here, so I don't have to write the equations out 30 times. So I've got the first node, the middle nodes, and the last node, all slightly different. This part right here is just trying to snap the left endpoint. When I simulate it, this is what V0 does. It kind of goes up and down like you're snapping a string. When I do that, that launches a wave. Again, very, very different than the heat equation. Notice when I hit the right wall, I get a reflection. The right wall is a free endpoint. I get a plus reflection. The left wall is fixed at 0. A fixed endpoint gives me a negative reflection. And let's try that again. So starting over again, I snap the left side. That creates a traveling wave that travels to the right, hence the name wave equation. The right endpoint is free. That right point snaps up and down. A free endpoint produces a plus reflection. A fixed endpoint, the left side is fixed at 0, produces a negative reflection. Now the reflection is called gamma. That's the reflection coefficient. It's equal to the impedance of the transmission line minus the impedance of the load at the right over the impedance of the transmission line plus impedance of the load. When I have a large resistance, basically infinite resistance at V20, that would be Z1 is infinity, I get a plus reflection. What that looks like is like the mirror image. There's this fictitious wave traveling from the right, coming left. When the two hit, it goes doubled in amplitude, and then the blue line keeps on passing off to the fictitious transmission line. The red line comes through, and you get a plus reflection. And that's kind of what we were seeing here. So starting out, there's a fictitious traveling wave coming in from the right. It's moving left, moving left, moving left. Then at this point, it's at 30. The two add together and jump to double the amplitude. Now the fictitious wave traveling from the right is what I see. It's now going back left. That's for Z1 equals infinity, a free endpoint. In contrast, if I fix the right endpoint, then I have a negative reflection. What happens is this looks like a negative wave traveling from the right. These two come together at the endpoint. The two cancel, so the endpoint doesn't move. And then the red line winds up over here. I get a negative reflection. So what it looks like now, I've got a negative reflection coming in on the left. At 0, the two cancel. And here's the negative reflection then appearing in this window. So what that means is that if the right endpoint is too loose, I get a plus reflection, like you just see here. If it's too stiff, I get a negative reflection. So that brings up a question. What's the Goldilocks number? What do I do to make the reflection 0? Now when you take 351, you can calculate that. Any wave, any transmission line has an impedance. When the impedance at the endpoint matches the transmission line's impedance, I'll get no reflection. That you can calculate. In MATLAB, I can find it using numerical methods, using trial and error. So what you do is take this number right here. This is 1 over RC. If R is really, really large, this becomes a small number like 0.01. If R is really, really small, then the right endpoint doesn't move, and this becomes a big number. What number creates no reflection? And that's kind of trial and error. In 351, you can calculate it. In this class, you just use trial and error and find it. So what I'm going to do, I'm just going to run this for 7 seconds. I want to have it run long enough that I can snap, have the wave come down, hit the right side, and reflect. Oops, 7 seconds wasn't long enough. I'm going to speed it up a little bit. That's increased dt, and run out 15 seconds. I want it to run long enough that I hit the right endpoint, then see the reflection. On your homework, just do a screenshot at this point, long enough that I see the reflection and come back. This is a plus reflection. So if I go down here in my code, this number right here is the right endpoint. So I've got my transmission line, the resistance on the very, very far end, the right side, is what I want to adjust. What's happening is I have a discontinuity. The transmission line goes out to 30, then stops. That discontinuity, that stopping, causes a reflection. If I make this number too large, like let's make it 100, what happens is instead of getting a plus reflection, now this right endpoint will barely move. Or numerical problems there. Let's make it 20. Now the right endpoint barely moves. That 20 is too big. I have negative reflection. So 20 is too big. 0.01 is too small. Let's try different numbers. Let's try 10. I launch it on the right. Notice the right endpoint will move a little bit more. That's because the 10 means it's less stiff. I still have negative reflection, so 10 is too big. Let's try 5. And that's not too bad. I still have negative reflection, so 5 is too big. Let's try 2. And this is kind of what you'll be doing in the homework as well. 2, I have a plus reflection. So 2 is too small, 5 is too big. Let's try 3.5. That's pretty close. If I do it right, there's almost no reflection. So now if I let it run longer, I can see what happens. I snap the left side, it comes down, hits the right side, and almost all the energy is absorbed in that resistor. I still have a wave coming back left, hits the left side, causes a negative reflection, that comes back to the right. On the right, almost all the energy is absorbed. So by terminating the right side with the right resistance, I can get rid of the oscillations. That's one of the things you try to do in EMAG with wave equations. Try to stop the oscillations. Try to stop the reflections. And there's a couple reasons to do that. For example, here, if I make the left endpoint being a sine wave, this is kind of simulating the wind blowing or an earthquake or the wind shaking a skyscraper. If I have a slight sinusoidal oscillations and I have the right endpoint causing reflections, I start getting the wave energy comes down, bounces, reflects, bounces back and forth. I start getting standing waves. That's kind of what happened at the Tacoma-Narrows Bridge. This is the wave equation when there's no place for the energy to go. The left endpoint is stiff, the right endpoint is free. And those large oscillations, those large standing waves, will eventually snap the bridge, make the building collapse. If it's a transmission line, the voltages get too large. If, in contrast, I terminate this correctly, then what happens is I have wind blowing, it excites the line, but instead of the energy bouncing back and forth, the energy is absorbed on the right. So if there's no reflection, there's no standing wave. So there's a couple reasons you might want to analyze wave equations and figure out how do you stop the standing waves. For example, if the car is stuck in traffic, if you have large standing waves in traffic and the cars come to a stop, you get traffic jams. If the building's swaying during an earthquake or a windstorm, if it's too large, you'll start having windows popping out or the building collapses. Bridges oscillating can cause metal fatigue, cables to snap, the bridge to fall. Transmission lines galloping. The lines touch, you'll get sparks. They hit the ground, you'll get sparks. The lines break, people are out of power. And circuit board traces. If I start getting, we'll show you that in a sec. Transmission line effects are problems on circuits as well. To get rid of for buildings, this actually is part of the ways they design skyscrapers. In the roof, that's where the discontinuity is. Again, I got energy travels up, hits the roof, bounces back down to the ground, sees the discontinuity, reflects, bounces back up. In California, a lot of the buildings are actually moved back and forth. That breaks that stiff endpoint and allows a little bit of friction. Some buildings, they actually add an oscillator or a water tank. As the building sways back and forth, this is causing the water to slosh back and forth, dissipating some of the energy. Some will have a little pendulum swinging back and forth. And that tries to counteract and dissipate the energy at the roof as well. On circuits, the circuit board we use in 376 is a little microprocessor similar to an Arduino, a Raspberry Pi. If you look at the voltages at really high frequencies, this is at 1.6 megahertz, for example. This is what the voltages look like. It's supposed to be a nice clean square wave. It's not. This ringing is real. What that's due to is the circuit board trace looks like a transmission line. At really high frequencies, I've got inductance. I always have inductance. Inductance is LDIDT. At really high frequencies, it starts to matter. and I have a capacitance. Again, the trace to ground creates a capacitor. Those two together give you transmission line effects. What you're seeing is the wave hitting the right side, right end of the transmission line or the circuit board trace, comes back, reflects, hits the right side, reflects, hits the right side, reflects. If this voltage gets too large, I'll get false triggers. That what's receiving is going to think I just sent a 1, then a 0, then a 1, then a 0, then a 1. Give a computer false data and you get gibberish. It quits working. The higher the clock frequency, the bigger the transmission line effects. So that's part of the reason that 351 is required for electrical engineers. It's a really good course for computer engineers as well, because clock frequencies keep getting higher and higher. As they get higher, you have to start designing circuit boards from a transmission line effect. NDSU has a plug for 2 courses. NDSU offers 2 fairly unique courses taught by Dr. Broughton. One is signal integrity. The other is for design for electromagnetic compatibility. What those courses look like is how do you analyze a circuit from a transmission line standpoint, and how do you design a circuit so that you don't get the transmission line effects, you don't get reflections. It also applies to antennas. At DC, electricity travels through a wire. At high frequencies, it's in the field around the wire. Put 2 wires side by side. If the fields overlap, I have crosstalk. Spread out the wires to have an antenna. So a circuit that behaves one way at low frequencies behaves like a radio transmitter at high frequencies. These courses also look at how do you design a circuit so it doesn't transmit, and from duality, also doesn't receive. And to support that course, we are very proud to have our very own shield room. This has a little bit of background. This used to be the governor's shield room of North Dakota. It's a big metal box. Back from physics, if there's a perfectly conducting metal sphere, there should be no electric fields on the inside. So what this is for is that if World War III would ever break out, the governor goes inside the room, closes the door, and the governor is protected from electromagnetic blasts. Since then, they've decided that they want the space more than the governor, so we got the room. What we do with it is put your circuits inside the room, close the door. Anything that you measure inside the room comes from inside the room. So that way I can measure how much your circuit's radiating. So at the start of the semester, when you're taking one of Ben Broughton's courses, you can measure how much your circuit radiates, then modify the circuit to reduce how much it radiates. At the end of the semester, close the door, measure the new improved circuit, and see how much you reduce the radiation. And from duality, what I can also do is put a computer in here. Hit it with radiation. If the radiation is too large, the computer will quit working. Do some tricks from that course, and then see how I can design it so the computer can operate at higher magnetic electric fields without failing. So that's a plug for 2 courses, 2 very, very good courses to take. It's very applicable to industry as well. Clock frequencies keep getting higher and higher, meaning circuits start behaving more and more like antennas. So electromagnetics, electromagnetic compatibility, and signal integrity are 2 very good courses if you're ever dealing with an area where the clock frequency keeps getting higher and higher, such as computer engineering. And 2 courses I highly recommend. That should get you through the homework for week number 8, Electromagnetics, where on the homework you're looking at, given an inductor, find the voltage from V equals L di dt, and for a circuit similar to this, write the differential equations, and then find, at a resistor at the end, find the resistor to terminate it to get rid of the reflections. That's week number 8 for ECE 111.